Look at these four objects: a carbon steel bolt, an aluminum can tab, a stone, and a piece of copper wire. If all four fall into the product stream of an industrial feed mill, which one will the magnetic separator catch? The carbon steel bolt is the only one that reacts. Carbon steel and iron are ferromagnetic, meaning they respond strongly to magnetic fields. People often assume a magnet acts as an all-metal filter. Aluminum and copper are non-ferromagnetic, and an ordinary industrial magnet will simply let them pass. Raw agricultural commodities are not harvested in sterile environments. Grain passes through combines, loaders, trucks, and massive elevators. A 10-gram piece of steel seems insignificant compared to hundreds of tons of grain, but machinery does not care about batch weight percentages. If that steel hits the wrong mechanical interface inside a high-speed roller or hammer mill, it causes instant jamming and damage. A feed mill magnet functions as a highly specific physical filter designed to prevent catastrophic mechanical failure. A modern feed mill operates on an immense scale, processing vast volumes of raw ingredients every day. This logistical chain creates numerous vulnerabilities. Between bulk deliveries, storage silos, and outdoor conveyors, foreign material has multiple entry points before processing begins. Once inside, the material enters a labyrinth of handling equipment. Belts, pulleys, and augers move the grain through the facility. If that aluminum tab or copper wire falls into a conveyor here, the magnetic controls are blind to them. They will travel straight toward the knowing equipment. Recognizing the physical limitations of the magnet allows operators to look past its role as a simple filter. The critical interception of a steel contaminant happens within violent torrents of fast-moving grain rushing past the equipment. Magnetic attraction decays as distance increases. If a deep bed of grain flows past a magnetic plate, a steel object traveling in the uppermost layer, farthest from the surface, might not feel enough pull to drop out of the stream. High product velocity dictates how much time the object spends in the capture zone. Rapid flow gives the magnetic field only a fraction of a second to grip the contaminant. Then there's the shape and mass of the object. A heavy carbon steel bolt tumbles through the grain differently than a thin steel shaving, altering how and when it contacts the magnetic surface. System design matters. True protection relies on engineering the correct product depth and flow rate, rather than relying on magnet strength alone. Because no single machine can separate every type of foreign material, feed mills employ a layered defense network. Screens and scalpers act as the primary physical barrier, blocking oversized objects from proceeding further into the plant. Destoning equipment addresses dense contamination, using gravity and flow behavior to drop heavy rocks out of the grain. Aspirators apply precise air currents to blow away lighter, non-grain debris. Every separation technology exploits a specific physical characteristic. The magnet is the instrument assigned to magnetic susceptibility. Ferrous contamination often originates from within the factory itself. High-speed processing causes internal machine components to slowly grind down, releasing fine steel wear particles directly into the product flow. Industrial vibration loosens hardware, dropping broken washers, nuts, and fractured machinery parts onto the conveyors below. Positioned directly in the flow path, the magnetic separator acts as a witness to this mechanical decay. This turns the routine task of cleaning the magnet into an operational data collection event. Operators establish an expected baseline. Collecting a small amount of fine metallic fuzz over a set period indicates normal friction and wear, but a sudden break in that baseline demands attention. If an operator opens the separator and finds fresh steel shavings or half of a broken washer mixed into the dust, the pattern has shifted. Instead of throwing the fragments away, they characterize the nettle, map the upstream machinery, and trace the feed pathway backward. By identifying the specific size and shape of the fragments, the team identifies a failing conveyor component and replaces it before it shatters completely. Treating the separator as a simple waste bin ignores its primary utility as a monitoring tool. The specific profile of debris recovered from the surface reveals the internal status of machinery that is otherwise hidden from view.